We're starting. Oh, I thought you were raising it. Okay, so we are in 7.2. Trig integrals and trig sub. So last time, towards the end of the class, I introduced trig sub to you. We did a couple examples. Just a recap on trig sub. So there are some expressions that we can see, sort of like the difference of squares or the sum of squares, that we can put our Pythagorean identities on top of them to figure out how to do integrals by substituting things and collapsing two terms into one. So these expressions were guys like this, as well as that guy. Each of these went with it, had with it a substitution. Do you remember what the substitution for this guy was? Yeah?
Secant squared theta minus 1.
Well, you're using the identity secant squared theta minus 1. So secant is kind of in the position of x. 1 is kind of in the position of a. Of course, here a is a constant, non-zero constant. So what would the actual substitution be if you're doing a trig substitution?
A secant theta.
You'd set a secant theta, right? Because you are taking advantage of the secant theta minus 1, secant squared minus 1 identity, right? What about this one? So what identity would this remind you of? The constant times the function squared. Yeah, like 1 minus sine squared will collapse into cosine squared. So x is equal to a sine theta. By the way, x equals a cosine theta is also possible, but conventionally we don't normally use it because it introduces a negative sign. Some people don't like that, but there are actually situations where I think doing a cosine substitution actually makes the situation a lot simpler. What about this guy? It's tangent, because this is reminding you of tangent squared plus 1 equals secant squared. Or in general, a tangent squared plus a squared is equal to a squared secant squared. So that guy gives you a tangent substitution. Now there's necessary, so this is for the substitution. There's a necessary step if you're doing an indefinite integral for the back substitution. Now how you sort of figure out the back substitution for this guy? What did we do to figure out? If I have an answer now in thetas, how do I change it back to x? What do I use?
Make a right triangle.
You can make a triangle, so for example here, you realize that secant theta is equal to x divided by a. This kind of forces on your right triangle based on SOHCAHTOA. And you know that secant is just 1 over cosine. Cosine is adjacent over hypotenuse, so this guy's actually hypotenuse over adjacent. So this would be the hypotenuse, that would be the adjacent, and then if you find that side with Pythagoras' theorem, it turns out being x squared minus a squared. That same phrase that you saw here, but with a radical on it. Similarly here, you can create a triangle. This would tell you that sine theta is equal to x over a. That's opposite over hypotenuse, so this is opposite, that's hypotenuse, and so this would be a squared minus x squared by Pythagoras' theorem. Similarly here, you realize that your tangent theta is equal to x over a, so then you can set up a triangle. That's opposite over adjacent, that's opposite, that's adjacent, and so Pythagoras' theorem will tell us that that would be a. And that being said, once you set up one of these triangles, you can talk about any of the trig functions in terms of x's, right? So knowing that secant is x over a, from this triangle I can figure out what the sine is. That's going to be opposite over hypotenuse. What is the cosine? Adjacent over hypotenuse. What is the tangent? Opposite over adjacent. Right? I can talk about all the other trig functions now. So in my answers in a bunch of trig functions, I can literally use this triangle to translate each of those trig functions into functions of x. Okay? So that's this step. This step, again, so this is what makes it trig sub a lot more annoying than regular substitution because it's not just like, oh, just replace u with whatever you said it was in the first one. It's not going to work. So you'd have to go through this guy, which in the cases of, I mentioned this last time, in the case where we have a definite integral, I would not go through the back substitution phase. I would just change the limits and then plug in thetas instead of x's. Okay? But that was the basic structure of how we're going to do our substitutions. And I think I want to do a few more examples. So we'll do that and then we'll talk about just some recommendations on applying this method. I think we did x squared over the radical of 4 minus x squared, yes? The integral.
The last integral was 1 over 1 plus x squared. Yeah, we did that one.
And I also did x squared over the radical of this. Did I do any others? I don't remember. I did 1 over x squared times the radical of x squared minus 3. All of that in the denominator. Was that all the examples I did?
Yeah.
Because I was kind of jumping around. We were running out of time, so I was kind of doing, okay, this one was probably kind of short, so let me do this. So I didn't do my examples in the order I wrote them. Okay, so I just wanted to make sure which ones I actually did. Okay. So let's do this one. Ideas. So I see that integral. I would actually take a couple seconds just to make sure, but I would actually look at this and like, can I use the power rule? No. Can I use substitution? No. Right? You always want to think that the easiest way possible, right? So there's no way to simplify this to use the power rule because there's a plus under the radical. I can't distribute radicals across sums. There's no way to use substitution because if I wanted to do substitution, I would want to substitute this expression, but the derivative of that is 8x. I don't have an x anywhere, right? Clearly, if there wasn't like an x in the top or something like that, I could have done substitution. That would have been fine. But that just wouldn't work here. So what are our options?
Is x squared 2x in a way? Or like,
I could think of this as dx over 2x squared plus 1. That's fine. Now what?
so a is 1. So it's like, I don't know if this is right, but like, since it's like x squared plus a squared, we could use the tangent theta thing.
Exactly. So this is a tangent substitution because this is 1 squared. Right? So now it's like instead of x, I have 2x, but again, constants are never really a problem when we're doing substitution, right? We can always factor them out. So in this case, I would do a trig sub. It would look slightly different from regular trig sub because I wouldn't just say substitute x, I would actually substitute 2x. So I'm going to set 2x is equal to a tangent theta. Right? My 2x is like my x in the general trig sub rules. In other words, my x is just 1/2 tangent theta. And just like with any other substitution, we need to figure out what the d's are. So this means I would differentiate. The derivative of x would be 1/2. The derivative of tangent is secant squared d theta. And now I'm just going to substitute all of these back into the original integral. So my dx becomes this guy, 1/2 secant squared theta d theta over the radical of my 2x is now tan theta. So that's what that becomes. Now what? No, we didn't integrate yet. We don't back substitute until we integrate. How would I integrate that? I just did a substitution, so I rewrote this function as that function. Now, how would I integrate that?
You have tangent squared plus 1 secant squared.
Tangent squared plus 1 is just secant squared. Literally the whole reason why we do a trig sub is to get the sum of these squares to collapse into one thing by using a trig identity. And that tangent squared plus 1 is directly a trig identity. That is just secant squared. So that guy is going to cancel with one of those. And technically, this would give you an absolute value, so depending on the limits, you might have to split things up and put negative signs when the absolute value calls for it. But for now, we're doing the general. Assuming we're in the first quadrant and everyone's positive. So, yeah. So this would be 1/2 secant theta d theta. So I had this, power rule couldn't work, substitution couldn't work, did a trig substitution, it got to this. It looked scarier at first, but then I applied my trig identities and now it just simplifies. So that, this guy we actually know how to do. What's the integral of secant?
Ln absolute value secant x. Wait. Tan x? Or no?
Plus
Plus.
tan.
Oh, yeah.
I have a question.
Yes.
Doesn't it just cancel out both of the secants since it's secant squared and secant squared?
It's not secant squared, it's the radical of secant squared. There's a radical. So we have that. So that's actually the antiderivative. The problem is that's the antiderivative in terms of thetas. The original question was asked in terms of x, so now we have to go through that whole back substitution. So now we're not done. By a long shot, we're going to have to figure this out. So we know at this point that our tangent theta is equal to 2x. I would think of this as 2x over 1, so that's my opposite and my adjacent. So that leads me to this triangle. So my opposite is 2x, my adjacent is 1, so the sum of those squares square rooted is the hypotenuse by Pythagoras' theorem. And so from that, I could figure out secant. Secant is just hypotenuse over adjacent. So that's 4x squared plus 1. And my tangent I already know, my tangent is 2x. So this would become 1/2 ln of my secant, which is this guy, plus the tangent, which is just 2x. And that's your answer in x. And again, you can check if you differentiate that guy, you will get this guy. Yeah.
I just have a quick question. This is probably like wrong for some reason with the trig substitution, but when we get to the point 1/2 integral 1/2 secant squared theta over square root of tangent squared theta plus 1,
Yeah.
yeah, right there. Doesn't that look a lot like a derivative of a hyperbolic trig function?
Which one are you thinking?
What was that? Cosh, I think. Like, would that work or not?
What was the derivative of cosh?
I think u prime over the square root of.
Oh, you're talking about cosh u?
Sorry, yeah. Wasn't it u prime over the square root of u squared plus 1?
No, I think that's
And
Oh, sorry. Well, yeah, doesn't it look like an inverse?
So this is cosh inverse?
Yeah, sorry.
Yeah,
Could it work that way or not?
it could work that way, yeah.
Okay,
So you could actually use hyperbolics here.
okay.
But we've already been over that, so I'm teaching you tricks up.
Okay.
So there are some of these where I know you know the answer by other means. Like I did that whole integral of 1 over 1 plus x squared. I'm just trying to illustrate the method to you. But yes, if you realize that this is a hyperbolic, I would do the hyperbolic. Like I said, I avoid trig sub if at all possible. But here I'm teaching you about trig sub, so I'm going to show you some things using trig sub. So that's how you do this using trig sub. Another example.
So if you did use the inverse cosh, how do you get your answer back into x? Oh wait. Never mind, actually.
Yeah, you just say u equals 2x, then this is du, you get cosh inverse of u, and then you just plug in 2x. So it would be like cosh inverse, it would be like I have cosh inverse of 2x plus c. Another example. Okay, ideas on this one? Yeah?
Can you like factor out, like can you factor the denominator inside of that?
Can you factor that? X squared plus 4x plus 8?
I don't think it's.
Two numbers when you multiply, you get 8, you add them, you get plus 4. You can't really factor, but there's another kind of manipulation you can do. What else can you do with quadratics?
Complete the square.
Complete the square is one thing you could do. I can complete the square of this guy. That's going to be x plus 2 squared plus 4. Because that gives me a plus 4, then need plus 4 to get 8. So that is actually equal to that. And again, technically, yes, you could do a sinh inverse substitution here, but let's do it the trig sub way. So again, this is just like a variable squared plus a constant squared. This is really 2 squared. So I would set my x plus 2 is equal to 2 tangent theta. In other words, my x is equal to minus 2 plus 2 tangent theta. So my dx would be 2 secant squared theta d theta. I'll plug these back in. So this would become 1 over my x plus 2 is just tangent, so this is 4 tangent squared theta plus 4 under the radical times my dx is now this guy, 2 secant squared theta d theta. This just becomes 1 over, that's 2 secant theta times 2 secant squared theta d theta. Very similar to the last one, except you don't have a half. So this is just the integral of secant theta d theta. It'll actually, our triangle will actually look different though. So I can't use the last answer. But that is the answer to the antiderivative. But now I have to do this triangle. I know that my tangent of theta is x plus 2 all over 2. So that's my opposite and my adjacent. And then this guy is going to be that x plus 2 squared plus 2 squared. And so this would imply that my secant is hypotenuse over adjacent. So then this equals, now we just go back and plug it into here. So it's just ln of the secant plus the tangent so that would be your answer. Which technically, using the log rules, I could just write this as this. Plus c. This is me just thinking of all of these guys over 2, and I know a log of division is just going to be log of the top minus log of the bottom, which would be ln 2, but that's just a constant, so that will be put in the plus c. So more than likely, if a problem like this was in your textbook and they did it using trig sub, they would write the answer as this and not as that, and you'd probably wonder, where did the half go? They just thought of it as ln of all of this all over 2, which breaks into ln of this minus ln of 2, and then that minus ln of 2, they're like, oh, that's just a constant, put it in the plus c. So it would more than likely look like that in your textbook. Let's do another example. But yeah, for the record, the last 2 examples I did, we could have used hyperbolic, inverse hyperbolic trig functions to actually solve them. But what about this one? It seems innocent, but it's not really just a square root. Right? Now it's a square root cubed. Right? So that kind of dashes all hopes of, oh, just look at it as a tan inverse, or oh, just use a hyperbolic trig function. Doesn't really apply anymore because of that little pesky 3 over 2. So a trig sub can help us here anyway. So it's a little annoying, I think, in general, but there are times when it really comes in handy, and it's a very useful technique to know. So for example, in this case. So substitution wouldn't work, power rule doesn't work, hyperbolic substitution wouldn't work, inverse hyperbolic substitution wouldn't work because of that pesky little 3 right there. But again, I would recognize this here, x squared plus 1. My a is 1, and my x is x. This is just a tangent substitution. My x would just be tangent theta. So my dx would be secant squared theta d theta. And so now I'm just going to plug these guys in. So my dx I will replace with secant squared divided by, this is just tangent squared plus 1. Now what happens there is the tangent squared plus 1 will become a secant squared. So that will become secant squared theta to the 3 over 2. But now what happens is I can reduce the power here. And so now what I would actually have is I would have secant squared divided by secant cubed, which is just 1 over secant, which is, it's just cosine. Integral of cosine is positive sine, and so that's our antiderivative of this guy. Now we just do the back substitution. I know that my tangent theta equals x over 1 this gives me that triangle, opposite over adjacent, so this would be x squared plus 1 radical. And so that would be my sine function is opposite over hypotenuse.
So x over x.
And so then this guy I just replace with that. So ultimately the answer becomes x divided by the radical of x squared plus 1. And so that's an example of where your hyperbolic trig functions might have not been the best thing to do. Another example.
I have a question.
Yes.
How do you know when to, like, where to put the trig sub? Like, how do you know x is going to be equal to 10, like theta?
Oh, because of all those rules I had in the beginning. I know that if I see x squared plus a squared, I always put x equals a tan theta. If I see x squared minus a squared, I put x equals a secant theta. And if I have a squared minus x squared, I would always put x equals a sine theta. So here, I had x squared minus plus 1 squared. So it's a pattern that you're trying to match on top of all of these three things. So if this was a minus 1, I would have actually used this one and did a secant, right? And if it was like a minus x plus 1, I would have used a sine, right? So it's really, I'm really kind of trying to fit on top of one of these two patterns, one of these three patterns. Okay, ideas here? Do you guys know any hyperbolics that looks like that? Kind of out of luck there. Okay. What else? Well, see, now this looks like x squared minus a constant. So if I want to fit it on top of one of these guys, it will be the middle rule. So of course that constant I'm going to think of as a radical squared. So this is really not, well, let me just write that. X squared minus radical 3 squared. So now this looks like that, where my a is radical 3. So let's actually try a trig substitution. So my x here, I would just use that. It's going to be a secant. This is going to be radical 3 secant theta. Dx would be derivative of secant tangent. And now what I would do is I would change the limits. Definitely not going to want to have to go through the back substitution. So my second step, if this is a definite integral, change the limits. So when I get my answer in terms of thetas, I don't have to do anything else. I can literally just plug into the answer in terms of theta. So when my x is equal to 2, what's going to happen? That means I have here, this would mean I have 2 is equal to radical 3 secant theta. Or in other words, my secant theta is equal to 2 over radical 3. How do I solve that equation?
Cosine, square root of
It's
theta.
just cosine. Notice that this would mean my cosine of theta is just going to be radical 3 over 2. What does that mean my theta is? Cosine of what?
Positive.
Five.
Five and three.
Copy it.
Remember that table in your head?
Yeah.
1, 2, 3, 3, 2, 1. So it's the first column. This guy here's pi over 6. That's 30 degrees. What about when x is equal to radical 3? Then that would mean that radical 3 is equal to radical 3 secant theta.
When you can see the
So that would mean that you ultimately you would get cosine theta equals 1. What's the smallest number that you know that cosine theta equals 1? 0. So I can rewrite this now as a trig integral where those are my new limits, 0 to pi over 6. This is why I did that trig recap. It's going to be important. Like that's not even the point of the problem. Like, okay, so now I'm going to do the new limits from 0 to pi over 6. And what's this guy going to become? My x squared minus 3. So basically this is going to give me 3 secant squared theta minus 3 in the top. Over my x is radical 3 secant theta times my dx, which is radical 3 secant theta tangent theta d theta. So this guy would just turn into basically the radical of 3 tangent squared theta. So this cancels that cancels that. This cancels that. And so basically now I have radical 3 times integral from 0 to pi over 6 of tangent squared. How do I integrate tangent squared?
Oh, is it the UV thing? Or actually probably not.
No. This is from like the first section where we're doing secants and tangents.
It's like cosecant or something.
No. You actually apply an identity first.
Secant squared minus 1.
Tangent squared would become secant squared minus 1. And each of those I can differentiate. The integral of secant squared is tangent because the derivative of tangent is secant squared, and that just becomes theta, and this is between 0 and pi over 6. So now I'm going to plug these guys in. So fundamental theorem of calculus comes into play, and so this would be radical 3 times tangent of pi over 6 minus pi over 6 minus tangent of 0 minus 0. What's tangent of pi over 6?
square root 3 over 3.
Right, it's 1 over radical 3, which is the same as square root of 3 over 3. Again, you just think of that table, 1, 2, 3, 3, 2, 1. So it's going to be a half divided by radical 3 over 2. The 2's are going to cancel, so it's 1 over radical 3. Minus pi over 6, tangent of 0. It's 0, because it's just sine over cosine. Sine of 0 is 0, so it's 0. And 0 is 0, so that's that. So you can think of this as 1 minus radical 3 pi over 6. Is going to be the answer.
Oh, I have a quick question. So, up there with the integral from 0 to pi over 6, yeah, that one. Where does that square root of 3 tan squared theta become just tan squared theta?
I split up the radical, so I think of this as the radical of 3 and the radical of tan squared. So that just gave me tan squared. That just gave me tangent. Then I took another tangent, and that's the tangent squared. This radical 3, it moved out in front.
Oh, I didn't see that part. Got it.
So when you integrate with limits, there's no plus c at the end?
Right, there's no plus c. You just apply the fundamental theorem of calculus, you plug in the top number into the function, minus plug in the bottom number into the function, and you subtract these. And you see here, I didn't have to go back to the triangles and figure out x's and get something really messy and plug in the old limits. I would highly recommend that you actually just change the limits. Whenever you realize that, hey, I'm going to need to use a trig sub here, and it's a definite integral, just change the limits. Trust me, it'll cut your work in like a half. Yeah.
But how do you know what to change the limits?
If you know you're doing a trig sub, always. That's my recommendation. Always change the limits. If you're doing a trig sub, always change the limits. Yeah.
So like, you know when you were changing the limit and you did radical 3 equals radical 3 secant, how do you know it goes to like cosine, like
Because I would divide both sides by radical 3, so that's giving me 1 equals secant. But secant is 1 over cosine. So you cross multiply, you get cosine. Yeah.
With the Pythagorean identities, like the just sine squared plus cosine squared equals 1, can we assume that the 1 is squared, so like if we put a constant in front of everything, the a would be squared too?
Yeah, that's actually how you can think. So with if you have cosine squared theta plus sine squared equals 1 squared, the whole reason why this method works is the fact that I can just multiply everyone by an a squared.
Okay. So the constant is squared in that.
Yeah.
Okay. Alright.
Right, and again, this, remember, came from the circle, where that was the radius, so you always think of r squared on the other side. You always kind of think of the other side as a square anyway, because it comes from a circle.
The unit circle?
Yeah.
Okay.
To trig sub or not to trig sub? That is the question. Okay. Trig sub, again, it's kind of going to be one of the beefier methods. It will take a long time to actually work through everything because you have to pass into the land of trig functions. You might have to use trig identities and SOHCAHTOA and all that stuff while solving a problem. So it tends to take longer. So don't use it when you don't have to. So I'm going to talk about sometimes when you shouldn't have to use trig subs. When not to use. Essentially, when another substitution works, don't use trig sub. How do you know if other substitution will work? There are two cases. U sub will work if there is an odd factor of x in the function. Right? So that's one way you can, so for example, I think I did write out some examples here. So if I had, so you can look at all of these guys and let me show you what I'm talking about. So you look at a bunch of these. They're basically variations on the same problem. One thing you can notice, we did one of these, we probably did this one. one thing you'll notice, the denominator is always going to be radical of 4x squared plus 1. The thing is, here a substitution wouldn't work because you'd actually need an x for that to work, right? So here, you kind of use it. Technically here, though, we could have used also u equals sinh inverse. Two x equals sinh inverse of u. So I probably wouldn't. This is where another substitution would work. But I'm specifically saying u sub here. This could work, but u sub won't work. So if you remember your hyperbolic identities very well, you could use that here. But here, you can't really do that. But notice that this part where you want to use a trig sub, elsewhere in the function there's an x squared, that's an even power, so you need to use trig sub here. But if you see something like this, like there's an x cubed, and you have to use a trig sub. I would not use a trig sub. Use a regular u substitution. It will work out. Once there's an odd power, because you can always factor off an x, then you have a bunch of even x's that you can actually deal with. So let me just do that one as an example. As well as here, because that's an x to the fifth, I would use a u sub, not a regular trig sub. And it will actually make your life a lot easier. So for example, if I had that x cubed over the radical of 4x squared plus 1 dx. The fact that there's an x cubed there means that I can do a u sub. So I would actually do a regular u sub. So something like, I could even do a u squared if I wanted to. U squared equals 4x squared plus 1. And so now your 2u du would be 8x dx. And so you might say, okay, I have an x, but there's an x cubed here. You don't really have to worry about that because you can just write that x cubed as an x squared times x. Right? And this part will take out the substitution. Right? Now you might wonder, well, I still have an x squared left over. How do I deal with that? Use this equation and solve for x squared, and then replace it. So if I use this equation, I can solve for x squared. What would that give me? This would give me u squared minus 1 all over 4. And now I can actually do some substitutions. Here I know that a quarter u du is equal to x dx. So now I can just plug them in. My x squared is this expression. My x dx becomes a quarter u du. My denominator just becomes u. This guy cancels. I can move these quarters out to get 1/16. And that's my integral, which is trivially easy. And I won't need a whole back substitution with triangles to deal with that. So it turns out if there's an odd factor of x somewhere else in your function, a u sub will work. All you have to do is just do that u sub, separate one of the x's. The other even powers of x, you can use the original substitution equation to change them. So if there's an odd factor somewhere else, you don't need a trig sub. A regular u substitution will work. Yeah.
So how come though, like you said, we have to have an odd factor of x to use u sub?
Yeah.
How would it work if you had like an odd factor, an odd power under the radical and an even factor on top, or an even power?
Well, in that case, it would just cancel.
Okay.
And there are times when having an odd factor in the denominator can work. So if I had something like the x times this, but you might need an additional technique, that's why. So these don't always work out that cleanly, but sometimes you can do that, and what you can do is you can put the x, multiply by x over x, and then this takes out the substitution. And then you replace this expression here. But it turns out in this case, when you do that, you'd actually need another technique that is in the next section. In fact, you'll need partial fractions to complete. Would you need partial fractions? You would cancel. You'd have 1 over u squared minus 1. You'd need another technique. So you could actually use a hyperbolic there, or you could use the next technique, which is partial fractions. So another time when not to use. So when a hyperbolic sub will work. Sometimes that works, sometimes it doesn't. So don't use. But this is a soft term. The less forms you have to memorize, the better, I think. And also, another recommendation. If you must use trig sub, on a definite integral, change the limits. It's largely an optional thing, but consider it more mandatory on trig sub problems. Because it will save you so much headache to just change the limits in the beginning and not worry about the back substitution at the end. So those are some recommendations. You can try a couple more examples. We'll stop there, but here are some to try. Might put them on the quiz Tuesday. Try this one. See where you can get with this one. Minus x squared, minus 4x. Try also x cubed. Next time we'll do partial fractions. And we'll have a quiz on this on trig integrals and trig sub. And the homework is due for this because I finished everything about trig sub. This section.